Okay, so today we're going to look at the graphs of y equal to the modulus of a function, right? And we're going to look where the function is linear. In other words, it's a straight line function. So we'll start off with the most simplest of these functions. So let's consider the function y equal to the modulus of x. Now, we need to take into account that the modulus can differ depending on what the value of x is. And so like we did algebraically, we can say, well, when x is greater than 0, in other words, when it's positive, x will be x. And if x was negative, in other words, if x was less than 0, then we'd have to put a minus sign to make it positive, right? So that gives us two linear functions to consider. We need to consider the linear function y equal to x and also the linear function y equal to negative x. And we need to remember that modulus is always positive. And when we think graphically, anything that's above the y-axis or the x-axis where y is equal to 0, anything above this line is positive, right? So we, at this stage, for these simple linear functions, cannot get anything below the y-axis or the x-axis. So what we'll do is we'll start by sketching the graph of y equal to x. So y equal to x is pretty simple. It has a gradient of 1, and it runs pretty much like that. Now, just for interest's sake, I'm going to continue drawing it down below here, just so we can notice an interesting property about modular functions. Okay, from here we're going to consider, well, we could also have y equal to negative x. So y equal to negative x is just running in this direction. It just has the negative gradient of the, right, it runs something like that. And one interesting property that we can note is the y equal to negative x is actually just a reflection about the x-axis, right? So we've just reflected all the negative solutions from y equal to x. We've just reflected them about the x-axis. So all the y coordinates have just become, well, that were negative, have just become positive. Okay, let's move on to a slightly different function. So here we have the function y equal to the modulus or absolute value of a half x minus 1. And again, we need to consider that what's inside the modulus, well, it could either be positive or it could be negative. And if it's negative, we would just make it positive by putting a minus sign. And again, as before, we can consider two functions, or we can draw the function y equal to a half x minus 1, and we can just reflect it about the x-axis. So let's consider it that way. Let's sketch the function y equal to a half x minus 1. It has a gradient of a half and a y-intercept of 1. So we would be starting at negative 1 for the y-intercept. It's a rise of 1, a run of 2, and we can just continue the function like that. Okay, at this point we want to discard any solutions below the x-axis because we're not interested in negative solutions. The absolute value is always going to be positive, but we can extend this line and we can use it to consider what would happen if we reflected. And the important thing is we need to reflect about this point here, because this is the point when the line y equal to a half x minus 1 becomes negative. And we don't want negative solutions, we want positive solutions. So all that's going to happen is every point below the x-axis is just going to be reflected about the x-axis. And we can consider a point here would be reflected over here, and so on. And we could just, from this point here, and there we have the modulus. Now we would have to obviously discard the solutions below the x-axis because we're not interested in those solutions. Now, alternatively, we could, like before, have just considered, well, what if the modulus was negative? We would make it positive. To make it positive, we would have just said y equal to negative 1/2 x minus 1, which is just y equal to negative 1/2 x plus 1. And you can see the purple graph is exactly that function. It has a y-intercept of positive 1 and a gradient of minus 1/2. Now, we also can use this idea of graphical representation to sometimes show why we get solutions to certain problems and sometimes we don't. So if we take the example that we did from the last topic on modulus, and we look at worked example 5 again, we were given this question. We were asked to find the modulus of 2x plus 1 equal to 5. And algebraically, we were able to solve that we had a solution at x equal to 2 and a solution at x equal to minus 3. Now, alternatively, we can say that these are two functions. It's the function y equal to the modulus of 2x plus 1 and y equal to 5, and we want to know when these two functions intersect each other. Now, y equal to 5 is very simple. It's a straight line that runs horizontally at y equal to 5. And now we can consider the modulus function. So we can say, well, this is the function y equal to either 2x plus 1 or y equal to negative of 2x plus 1, which is just y equal to minus 2x minus 1. You can either do the positive one and reflect about the point that touches the x-axis, or you can consider the two functions separately. So 2x plus 1 has an x-intercept of plus 1 and a gradient of 2. So an intercept at plus 1, it's a rise of 2 and a run of 1, so something like that. And we can join the dots, something like that. We can also just continue down to the bottom, just so we can see exactly where this function is going to touch the x-axis. We can ignore the solutions below the x-axis, so these ones over here. And we can now also consider the function minus 2x minus 1. So it's going to have a y-intercept of negative 1, and this time it's a gradient of minus 2 plus 1. So we have down 2 across 1. We can join the dots. And there we get our function. And again, just ignore all the solutions down here because we're not interested in them. Now, if you have a look, we'll see we have two intersections here. And if we drop those down to the x-axis, we can see that those are happening at negative 3 and positive 2, just like the two solutions that we got. Now, in the same sense, we can take this equation, or this equation that we were asked to solve, where we had the modulus of x minus 3 equal to 2x. And when we solved it, we found that one of the solutions wasn't valid. So graphically, let's see why that's the case. So again, we could consider this as y equal to the modulus of x minus 3 and the function y equal to 2x. Now y equal to 2x is quite simple. It's just a straight line with a gradient of 2. So up 2 across 1. So that would be something like this. And I'm not going to extend the line below the x-axis because since we are talking with a modulus function, we're not going to have any solutions below there anyways. Right, now let's consider the function y equal to the modulus of x minus 3. This could either be y equal to x minus 3, and we could draw the straight line y equal to x minus 3 and then reflect it. Alternatively, we could consider the negative version, which is minus x minus 3, which is just minus x plus 3. And so let's sketch those two functions. So we have y equal to x minus 3. So we have a y-intercept of negative 3. And we have a gradient of 1. And so we can sketch this function like this. Right, again, I'm going to ignore the solutions below the x-axis because this is a modulus function. Okay, the negative version of this is got a gradient of minus 1 and an x-intercept of plus 3, which is over here. And we're going to get something definitely not like that, something more like this. And now visually and graphically we can see why we only got one solution, right? Because the line y equal to 2x only intersects this modulus at one point. It doesn't have a gradient shallow enough to intersect this modulus function twice. If the gradient had maybe been a half, we would have possibly got two solutions. So that's a wonderful use of graphically representing modular functions. It helps us to understand why we get and don't get certain solutions.